Good morning. Hi, everyone. Thanks for joining us today on this interesting and first session of its kind being run by the Faculty of Science and Engineering. Well, first of all, what I'd like to do is just very quickly give an introduction of background to today's conversation. So the University of Manchester is very much about world-class research, but it's also about our commitment to translating that research into real-world issues and addressing global matters. In fact, just recently, the university was named by the Times Higher magazine as #1 in the world for achieving work towards the UN's Sustainability Development Goals. A pretty impressive accolade, but it does reflect what we are trying to do at Manchester. It is about research and innovation and making things happen. So to celebrate that, the university decided to host these two exclusive events to showcase that impact, the impact of our science and engineering faculty, but through the prism of what we call our research beacons, the sort of flagship research for the university. Most of it, as it happens, is around the science and engineering community here. One in advanced materials and one in energy will be celebrated in these seminars. But today's session is about advanced materials. And I'm joined by three excellent guests today to help me navigate how advanced materials is making a difference. So today I'll be joined by James Baker, Chief Executive for Graphene at Manchester, Dr. Beanish Sadiq, Chief Executive and also founder of AEH Hydrogel, and Dr. Zeb Leeper, founder and Chief Executive of Water Cycle Technologies. And those latter two, it's sort of pride to say that they are recent graduates, doctoral graduates of the university, and now set up their own businesses working with advanced materials. But in particular, all three are, what links them together is that they are part of our exciting graphene community. So to progress with with today's session, what we're going to do is allow each panelist to introduce themselves, and each panelist I know has prepared a short presentation to illuminate and illustrate what their work is about and how we are working towards those goals of impact. And then we've been deluged actually with some questions from the audience. So thank you for those questions already, and those will come in, I'm sure, as our speakers progress. So give us some time to look at those after our speakers have spoken. James, so if I may, can I kick off with you, please, and allow you to introduce yourself and just, again, introduce your work to our audience today.
Thanks, James, and good morning, everybody. So I'm James Baker. I'm the Chief Executive of what we call Graphene at Manchester. What I want to do very briefly this morning is first of all, introduce you to graphene, how it all started here in Manchester, 2004, two scientists driven by curiosity, took some graphite, a pencil, and some sticky tape. And if you peel that over and over many times, around 15 times is the optimal amount, you can isolate a single atomic layer of graphene, of graphite. So what is graphene? It's got length, it's got breadth, but at one atomic layer thick, it's the thinnest possible material. So what, you might ask yourself? The two scientists involved in that then went on to receive the Nobel Prize for Physics in 2010, not just for that isolation, but as a 2D material, graphene has unique and different properties. 200 times stronger than steel, more conductive than copper, can act as a perfect membrane. So in terms of products and applications, it can have applications from aerospace to automotive, to battery, to healthcare. But more importantly, in the agenda today, it also can really support the sustainability agenda that we're all looking for. UK trying to go carbon neutral by 2050, here in Manchester by 2038. So a key area of research, but also commercialization, is how graphene and 2D materials can support that sustainability agenda. So what we have here in Manchester, as well as the science, we have the National Graphene Institute, the £61 million facility at the centre of the campus at the University of Manchester, bringing together that multidisciplinary research from physics to material science, to engineering, to biomedical. And today, not only are we looking at graphene, but over 100 other 2D materials. And in the future, in this whole agenda of advanced materials, imagine having almost like a stack of layered materials that builds multifunctionality into our products in the future. So we continue to do some great science around graphene, but also the broader advanced materials agenda. And the National Graphene Institute is supported by the Sir Henry Royce Advanced Materials Institute, all really progressing that advanced materials agenda. But my interest is less on the science, more on how we convert that science into products and applications. So in addition to the NGI, we have a second graphene facility, the Graphene Engineering Innovation Centre, or GEEC as it's commonly called. So what is the GEEC about? It's less about the pure science, it's more about converting that science into pilot production and scale up. How do we make graphene not by the gram, but by the kilogram or by the ton? But more importantly, how do we then mix that graphene into a composite, into a coating, into a battery, or into an ink or a formulation to develop these new products and applications? But as well as the science, we've developed a novel new innovation model. Traditionally, it can take many tens of years from the science discovery through to a product in the marketplace. And what we're trying to do here in Manchester, as well as that science, is look at that whole innovation model of rapid prototyping, scale up, a system I would call make or break. And for example, last week we held a hackathon here in Manchester, where we brought students from across the university and across the UK who came up with novel ideas and designs. And hopefully when we're out of the lockdown situation and COVID, we'll be in the lab making samples, making prototypes to accelerate those into products and applications. And again, you'll hear some of our speakers later today around some of the businesses that are now looking to take that graphene product or application into the marketplace. So what we're doing here in Manchester is not just the science. If you look at a scale of what we call technology readiness level, but system readiness level also on the two axes, we're trying to go from bottom left to top right to develop new products, new applications in partnership and collaboration with industry. So here in Manchester, there's not only chance to get involved in the science, in research, in the teaching, but there's also opportunity to be involved with industry, to create new industry, startups, spin-outs, well, not just spin-outs, but scale-ups, building both material but application in the supply chain. And what you'll increasingly see, and you'll hear some examples this morning, are increasing products on the marketplace where graphene plays a key role. So just to pick on a few that support sustainability, by adding graphene into concrete, can we actually get the equivalent performance from that concrete using less material, less steel, less concrete, so less CO2 footprint, but also cure quicker than it traditionally takes a concrete structure to complete it. And actually, as I speak this week, if you follow Twitter and LinkedIn, we're actually laying a complete floor of a gym in the UK using a graphene enhanced concrete. Lower material cost, lower material footprint, lower CR2, more sustainable for the future. Other areas where we're working include lightweighting, so taking weight out of cars, and you'll see on the bottom left there an example. But I don't know if you knew, but nearly every Ford coming out of the US now has graphene in the foam of the engine bay to take out weight, to manage to heat more efficiently, to reduce noise and reduce emissions and pollution. And again, I think you'll see more of that increasingly across both automotive and aerospace sectors in the future. And finally, as an example, what we're starting to see also is through the addition of graphene, you can start to recycle materials. A good example is that in rubber. So take your tires from your car, and if you, rather than scrap those tires, put them on a scrap heap and create waste, if you can take that rubber, recycle it, add graphene to it, potentially you can get a recycled product you can use for flooring, for matting, and other rubber products. And you'll hear two other examples this morning, one around food production, one around water, where graphene can really make a big difference in support of that sustainability agenda. So thank you for listening. Hope you've enjoyed the initial introduction, and hopefully from our next speakers, you'll get a little bit more about what they're doing to bring this whole ecosystem to life of companies not just doing the science, but companies who are creating businesses and startups here in Manchester. And if we can make that work, not only do we have the university, do we have the research, but I'm sure you've all heard of Silicon Valley. We're starting to create what I would call a graphene city, an ecosystem of companies who can accelerate their ideas, their concepts, their products to market to really create a sustainable future here in Manchester. So looking forward to answer any questions later, but it's my honour now to pass you on to Dr. Bina Siddiq, who will talk about her business and her startup here in Manchester. Thank you for listening. Thank you.
Yeah, morning. So if you just allow me a second. Okay, so our company name is AEH Innovative Hydrogel, and what is our vision? So we want to become Apple of agri-tech sector, and now we are working towards that. So sorry, I think there is a message, internet connection is unstable. It is just with, hopefully we'll be fine. So what I will do, firstly, I will give introduction about myself, because I know like lots of people who are attending this session, they are students. So probably, I mean, I can motivate some of the students. So myself, originally, I'm from Kashmir, Pakistan, part of Kashmir. So I came in 2008. I did my undergrad degree from Aston University. After that, I worked in industry for 2 years, just to get after that, I decided to do my PhD, and it was from Manchester University. So I got admission in a couple of universities, but I decided to go with Manchester University. One of the main reasons was like it's about research impact, like especially in material sciences. After finishing my basically, I was a PhD student. I managed to submit my thesis in 2 years and 10 months, and I got postdoc position. So lots of, I mean, postgraduate student or PhD, they do believe like they have to career path. I mean, to be honest with you, we used to think like if you're intelligent, you will just go to academia. So I decided when I received like postdoc position, then I decided go with like accepted it, and I went to University of Birmingham. But after that, I realized when I accepted that position, I was working as a postdoc. Then I realized it's like I'm more interested in commercialization of product. There are numbers of PhD students here. I mean, they will understand like academic research is slightly different to industrial research. So what I did, I decided to have a startup company, and then I found it. When I was to start a company, and it was like October 2018, but I started properly working on February 2019. So what our company basically do, so this is the product which our company is developing is like hydrogel substrate. If you guys are not aware about hydrogel, so hydrogel is basically a material that has more than 60% of water in the structure, and rest is polymer and other components in it. So I developed like hydrogel, and then I found it has application in indoor farming and outdoor farming beside medical application. So with indoor farming, if you guys are not aware of it, so indoor farming is basically when you grow crops or plants inside in water, or like in like other substrate media rather than soil. Why there is like a need to go with indoor farming? Because at the moment 9.9% emission are from traditional agriculture, and more importantly, if I just give you example, there are leafy green. If it grows in Spain and if it comes to Manchester, then it has a significantly higher carbon footprint than if it's shipped from Manchester to Manchester. So you have like food leafy greens to same city. And third important thing why it's indoor farming is important, because 70% of fresh water is used in agriculture, and unfortunately out of that 70% water, 60% get wasted. And then more importantly, by 2030, half of the population will be living in water stressed area. So how we came up, like what is our solution. So basically I have developed a substrate that has graphene sensor in it, and we are utilizing antibacterial properties of graphene in it. So indoor farming, basically when you grow plants, you need a substrate or supporting structure to support plant. At the moment, there are lots of substrate like peat, rock wool, but they are not sustainable, and they are basically a single most important like contributor of greenhouse gases. And the substrate we have developed, basically it's a hydrogel that has like graphene component in it, but it's a green graphene. So the way it works, the other way, I mean, in substrate is like there are lots of bacterial or algal growth when you grow in indoor farming, because when you use lots of light, then ultimately it increases the algal growth, and it reduce the yield of plants or crops in indoor farming. So with our product, because we have like some sort of substrate that has ability to tackle that issue, and it's also based on polymer based material that are biodegradable and environment friendly. So it means it has low carbon footprint with no waste disposal issue. And most importantly, this substrate, basically the one we have developed, it also has application in outdoor farming like traditional agriculture. So why it's important? Because the current substrate, when you use in indoor farming, mostly you just put on soil or like, and it remains over there for a number of years, and it's an environment issue. So with our substrate, it has application in outdoor farming. So once growers are done using in indoor farming, simply they can put in soil, and over there it reduces the fertilizer usage because it has special carbon and nitrogen component in it, and hence it reduces greenhouse gas emission. And it also reduces it also saves 60 to 70% of water, because 1 gram of our hydrogel has ability to hold 600 gram of water in it, and it releases to plants very slowly. So most importantly, it increases the soil fertility. So for example, in lots of South Asian country at the moment, soil fertility is major issue because of excessive use of fertilizer. So it also tackle it. So just to let you know about company. So when I started this company, I was just on my own. So with £0 in my bank account, but then subsequently I applied for a number of awards like Venture Further, Ali and Harari Graphene Enterprise Award and Shell Award. So from there I got seed funding, and because of that, I also got like when I was a runner-up for Ali and Harari Graphene Enterprise Award, so I got an opportunity to work with Ray, and I also got opportunity to work in Graphene Engineering Innovation Center. That is the most like from where basically was an important milestone for our company, and from there we are just going really like I would say moving forward really fast. So now we are around 11 people in our company, full-time or part-time, and then most importantly, our company has gained a significant traction. We win like after once I was in Geek, so I received like a lab space over there and support from James Becker and everyone out there. So then I managed to get 1 million Innovate UK grant and then pre-seed investment. And most importantly, now we have established relationship with potential customers and distributor, because that is the most important thing, because you are developing product, but then you need to find a real application. And for that, we are quite lucky, because there was a market gap and we managed to get like relationship with lots of customers and distributors. Thanks. So hopefully it's for 10 minutes. It's now about 10 minutes. Okay.
Yeah, thank you, Binish. That's a very that's an impressive story there, I have to say. And I think actually you and Zed therefore have something in common. You both were awarded Eli Harari Awards. So that takes us nicely actually into Zed now. So over to you, Zeb, and a bit presentation on your background and where you're from.
Can you guys hear me okay?
Yeah, loud and clear, Zeb. That's great.
Excellent. So yeah, I'm Seb Leaper, and I have recently completed a PhD in Manchester as well, and I'm founder and CEO of Water Cycle Technologies, which I'll talk a little bit about now. So just a bit about me. I was born in Watford, down south in the UK, and then came up to University of Manchester to study material science and engineering. I liked the idea of Manchester because it was far away from where I grew up, had a good music scene, good football, and had this thing called graphene, which had just about been discovered. It was the Nobel Prize was won the year before I went to uni, so the timing was quite interesting. I heard about it and I thought, maybe this thing is worth looking at. And actually, since then, I've stayed in Manchester. It's kept hold of me. I went on to do a PhD in nanoscience with the Graphene Now Nano Centre for Doctoral Training. So for those of you who are maybe looking at a PhD, a Centre for Doctoral Training, or CDT, it's kind of like a course in which, if you have a general interest in a subject, whether it's AI or graphene or something else, you can join this cohort. Usually they're quite multidisciplinary. So I was working with people who were from biomaterials, from maths, from physics, and then you get to choose projects based on your interests, and it's quite a good way to get into a PhD and have a bit more time to really find the right subject for you. So I chose a subject on water technology, and now I'm just finishing a postdoctoral fellowship called the Doctoral Prize Fellowship, which is coming to an end in July. But really, over the last year, I've been focusing primarily on my spin-out company, Water Cycle Technologies, which I'll discuss now. So my research interests, nanomaterials, nanotechnology. This is very broad category of applications, but a lot of innovations, I think somewhere I read 60% of innovations come from some innovation in materials and exploiting material properties. And now we've developed really amazing techniques to go and see materials on the atomic scale, which really opened up the field of nanotechnology. And so there's a lot of things like we take for granted, like in our phones, which are based on nanotechnology. So it's a very interesting area. My project I chose, I initially was interested in actually going into renewable energy, maybe solar or battery technology. But then I came across a subject on water treatment and read a bit more about the water crisis and felt compelled to spend the next 3 or so years studying this issue. And now with the company, I'm particularly interested in not just water recovery, alleviating freshwater scarcity, but also in minerals recovery. So actually finding what's in the water and taking it out so that we can reuse it rather than just throw it away and let it be dispersed into the environment. And so this technology that I've been developing is called membrane distillation crystallization, or MDC, which has the ability to do these things. So why water technology matters? Well, here are some facts about water, and you'll hear many. This one is quite interesting. 2 in 3 people experience severe water scarcity for at least 1 month of the year. So that's a majority of people around the world in both developed countries and developing countries. And what I like about this statistic is that it highlights the fact that what matters with water scarcity and water availability is not average values across an entire year. What really matters is the extremes. So, there might be parts of the world that are incredibly dry during one part of the year, and then there's too much rain in the other part of the year. And that's what matters. You can't survive more than a day or two without fresh water. So we need to, in a similar way to renewable energy, we need to level out the supply of water across the year. Meanwhile, 80% of wastewater produced annually is left untreated, that is kind of returned into the environment. That's enough water to fill the Persian Gulf. That's every year. And actually that number is quite an underestimate, because that's only what's reported. The real number is likely to be much greater than that. So there's this kind of disconnect between the amount of wastewater that we produce, and actually the availability of fresh water. And there's a human cost. You know, water pollution is costing the lives of 400,000 people every year in India alone. This is from industrial pollution, just discharging the water back into rivers, and it's a humanitarian crisis that we need to fix. So this is membrane technology has really helped alleviate this problem, and it's given us the tools to turn, you know, undrinkable water into drinkable water. But there are kind of limitations. So this is how it works generally. You start with a hydrophilic membrane, hydrophilic meaning water loving, and you tend to apply a hydraulic pressure onto the feed water. So this might be seawater, for example. And because of that pressure, it forces the water through this selected membrane. You get filtered water on the other side, and you get all the gunk and the brine and the salt that's retained on the membrane. The problem is this brine, this yellow arrow, because there's a limit to how much pressure you can put in before the membrane will break. And the more concentrated the water is, the more pressure you need to actually overcome something called the osmotic pressure. So as you filter water, if you imagine putting too much coffee in you're plunging too much coffee, the pressure is very high. And eventually, if you press too hard, then it will explode. Similar principle with membranes. So there's a limited recovery of water. So seawater, for example, when you desalinate it, typically you get a litre of seawater, you get half a litre out, which is fresh water for drinking, and then half a litre of this brine. And what do you do with it? Not only that, but these pressure-driven membrane processes require a lot of pre-treatment. So they're actually pretty complex operations and need regular cleaning, and that's cleaning often with chemicals which end up in this brine. And not only that, but it's prone to fouling. And so in some cases, these membranes only last for 3 months before having to be thrown away. And that's not a very sustainable solution. So this is kind of how this yellow arrow, this brine problem is solved currently. One option is just to dispose of it into surface waters, so back in the ocean or into rivers, as we can see here, which is a common practice in the desalination industries and also textiles. But this damages ecosystems. As I said, it has a high human cost and is increasingly expensive as regulation catches up with it. Another option is to evaporate the water away using these evaporators, but these are very energy intensive and very capital intensive because they need these high grade corrosion resistant metals because salty water is very corrosive, particularly at high temperatures. And another option is to use evaporation ponds. So this is a lithium mining company in Chile. The majority of lithium, which is, you know, powering your battery in your phone, this part of the world in South America called the Lithium Triangle. And they basically pump the water from the ground, which is rich in lithium, it's naturally occurring, and just chuck it onto the surface, and the sun evaporates away the water, and you get left with these crystals. It's a very slow process, taking 18 months before you actually get the crystals out, and it's very land and water intensive as well. So you need to have a solution which is cost effective, but offers this ability to recover the water up to 100% so that you can get these crystals out. And that's what I've been developing. So MDC operates in a different principle. You have slightly heated feed water. Now, this doesn't have to be high temperature. It can be 30 degrees if necessary. And instead of using a hydrophilic membrane, you use a hydrophobic membrane. So it's non-wetted. What that means is the liquid is unable to pass through the membrane, but it's still porous. If you have a lower temperature on the other side, then you create what's called a vapor pressure gradient. And it's the vapor pressure which is driving pure water vapor across the membrane. And then you get distilled water on the other side. And unlike with conventional processes where there's this limit to how far you can go, you can actually just keep recycling this brine further and further back, extracting more and more water up to the point of supersaturation, where you can collect crystals, basically. And you can use this to control the quality of the crystals. So this technology enables high recovery up to 100%. And ZLD stands for zero liquid discharge, which means that there's nothing going back into the environment. It requires little to no pre-treatment because of the hydrophobic membranes. It's kind of self-cleaning. Driven by low grade or waste heat as well, this temperature difference can be very low. And so there's waste heat available everywhere in air conditioning units, in industrial processes. It's really abundant and it's just not being utilized. And the crystal quality can be high as well. So for these membranes, they need to be highly porous, chemically, mechanically, and thermally stable. hydrophobic and scalable. So these are two methods of producing these membranes, one called phase inversion. You can see the spongy crumpet-like structure of the membrane there. And then another process called electrospinning, which creates this sort of spaghetti structure, which is very interconnected, highly porous. And we're actually developing both of these techniques and trying to look at the pros and cons of both. So where does graphene come in? Well, typically graphene membranes are made in this way. You have graphene or graphene oxide that's stacked on top of a porous support. And these black lines are the graphene flakes. And the gaps between the black lines basically control what goes past them. So you can change the distance between them so you can allow water to go through, but stop other things like salts and heavy metals, etc. And I started my PhD looking at this structure, but there are challenges with this approach. Mainly the fact that you're still, when you have a vapor permeation, you're still limited by the structure of the support layer. These membranes on their own, freestanding, are too thin and too brittle to really survive without a support. And so really you're kind of limited by the properties of the support anyway. There's also long-term durability issues, and eventually you get the channels blocking. And so I've actually been developing mixed matrix nanocomposites, which are actually very scalable, have better long-term performance, and can simultaneously improve the mechanical strength and the porosity of the overall structure. And so you can basically get better longer-term performance out of this structure. And so here's some approaches. So this is a phase inversion membrane. This is basically blending graphene and functionalized graphene into a polymer matrix. And you tend to find that there's a sweet spot where if you add too much graphene, the performance declines. If there's not enough, it's not so good. And somewhere in the middle is where you get this peak. And so similarly here, about 0.3% of the filler loading, you get this optimum in performance. If you add too much, then you suddenly get a reduction in your salt rejection. And so it's finding these sweet spots, and there's actually a lot of parameters to play around with here. I can't go into too much details about this because it's a bit intricate, really. But the electrospun materials are different still. This is the spaghetti structure, and now is becoming increasingly scalable. And I'm actually working in the Henry Royce very soon because they've got a large scale piece of equipment to build these. But here you've got commercial material and the membranes that we're developing, and you can basically double the flux. And that means that you can get twice the amount of water out of it with the same amount of membrane area. And the upshot of that is that you get cost savings. Not only that, but the mechanical properties are improved, which means it's more durable. So here's some videos quickly. But this has happened at the Geek. So I'm a big shout out to the Geek, as James mentioned. This was a trial that we did at the end of last year. And you can see here on the left hand side, this is our pot of graphene in solution. It's black, as you can see, just being pumped into this industry standard process, and we've been testing these membranes and are quite happy with the performance of them. So yeah, we've raised some money, not as much as Beanish. Beanish has done really well, but we're trying to get to where Beanish has now managed to get. We also won the Graphene and Ellie and Britt Harari Graphene Enterprise Award, winning 50 grand, and recently drew down 70 grand from the Connecting Capabilities Fund. We've also established desalination pilot projects, as well as working with 2 lithium mining companies, one in the UK and one in Chile. And so yeah, connecting with the customers and actually doing pilot studies is really crucial for our technology. Here are a couple of other videos just demonstrating dye removal. This is a sort of emulating textile wastewater treatment. Textiles are a big water consumer and they pollute a lot. And so with our system, you can get water vapor passing through, but leaving the dyes and the salts in the water retained on the other side. And so you can see the difference here in the color. And the other approach as well, which we're looking at, is beer dealcoholization. Because this is based on a vapor pressure difference, you have a different vapor pressure between ethanol and water. And so you can actually dealcoholize beer. So we're working with a local Manchester brewery to do some work there. So yeah, this is some recent stuff. We did a 6-week continuous pilot study to test our membranes. These are the membranes we made in the Geek. You can see some evidence of fouling on the membrane. This is sort of iron oxide scaling, but actually if you look at the stability, the performance was continuous throughout the whole time. We managed to enrich the lithium content by a factor of 20, but at which point we actually ran out of water. We needed to get more water from Cornish Lithium, our suppliers. So we're quite happy with those preliminary results, and we're working with them now to refine the lithium carbonate production. So in conclusion, yeah, we're developing graphene membranes in conjunction with MDC technology. With graphene, what I've found is that you can often get multiple benefits in one go. So rather than just looking for one engineering application, when you try to use graphene, sometimes you can get unexpected benefits. So the ability for our membranes to be both more hydrophobic and anti-fouling, but also more mechanically stable and more porous, means that the economics of it, bearing in mind the loading of graphene is very small, so only really adds about 0.5 to 1% of the material cost of the membrane, means that you can actually save money by using these graphene membranes. And that's really important when you're dealing with lots of high area membranes. There's lots of applications, and we're trying to focus now on particular ones that are most viable economically and meet the best demands. So lithium extraction is really crucial, as I said, to support the growth of batteries across the world. Desalination and dealkalization are some others as well. And now we're actively pursuing greater funding. We want to build up a team and have a bit more people and more expertise, because we've made a lot of progress recently, and we want that to continue. So thank you very much for your time, and I'm happy to answer any questions you might have. Cheers.
Thanks, Zeb. Amazing stuff there. That's first of all to Beanish and to Zeb. I have to say some amazing science and engineering there, and how you're applying that into real world applications and making a business and the seeds and market opportunities and everything else. That's incredibly impressive. And I have to say, well, thank you to all speakers, and back to you, James. I mean, this Manchester model and the ecosystem I think you're trying to develop, but clearly helping people like Zeb and people like Beanish to take that science, that engineering, and making it into a business. That's really compelling stuff. It's a powerful narrative this panel has come up today, and I have to say some very impressive stats. I mean, Zeb, you talk about this scarcity of water. That's quite an eye opener and a bit of a shock, really, that these things happen in today's society. And if I may, I think I may now look at some of the questions that are coming in from our audience, and I might start with a big one here. And it talks about the availability of graphene and the technology around graphene to the majority of cities and communities. I don't know, James, what do you think to that? I mean, it harks to a question: can this nanoscience, can graphene, can you scale up? Can Beanish, can Zeb, and people like them, the entrepreneurs that are driving the technology forward, can they access the rest of the world with that? What do you think?
So it's a fairly broad question. I think, first of all, point out graphene 2004 to today sounds a long time for many people, but 17 years is still relatively young for a new material. So we haven't got all the answers, but just from the example from Beanish and Seb today, you are seeing already applications being developed, seeing graphene being produced by the gram, by the kilo, by the ton. So first of all, it's not something that's just in Manchester, it is global. So graphene is being researched around the world, not just graphene, but this whole series of 2D materials. But also companies are making graphene again around the world. So there is a global supply chain, and there's different ways of making graphene from graphite or from, for example, methane. So it is a very much an international study and an international global material. What we're seeing in Manchester, though, is people are working. We work with partners, startup spin-outs, and we've listened to two today. But we're also working with companies from Americas, from Brazil's, America, from China, from Europe. So very much is a broad international subject. So for me, the challenge is really how do we collaborate, both academically, but also with industry. We work with a Spanish steel company who are looking at developing a new products outside of steel, as an example. So I think it's a great area where we can have partnerships and collaboration from outside of Manchester, outside of the UK. But what we're trying to create is some sort of distinctiveness of Manchester. Through the National Graphene Institute, the GEEK, the Henry Royce you've heard about today, but also our student population. Actually, we want the future entrepreneurs. Seb and Beanish are great examples of people who have studied here, done their undergraduate, postgraduate, and then gone on to hopefully create businesses for the future. So yes, I think Manchester's a hub, but we are looking for international partnerships, relationships, outside of Manchester and across the world going forward.
Thank you, James. Brilliant. And then, if I may, just that point there, you mentioned students. As a question, actually, an interesting question about graphene and its role towards the benefits of civilization and the economy. And if I may, actually, if I take that to Sebastian and maybe Beanish, as the point came across, Sebastian, you seem to be like a graphene baby. You've grown up with graphene. It is something that, unlike people like me and James, it still seems relatively new to us. James says it's 17 years old. That's a drop in the ocean to us. But to you, you've grown up with graphene. I just wondered, as a student, as you enrolled on your course, did you ever think this nanotechnology, this material, and the work you're doing around it could be so impactful to the world around us?
Yeah, I think if I were to go back in time to my 17-year-old self, where I'm at now is kind of like the sort of dream, really. I kind of thought maybe this was. I never really thought of certainly never thought of myself as a PhD student. I remember when I was 17, I thought, bloody hell, PhD is something for geniuses and crazy people. And then as I got more into research, I got a bit of a taste of research in my undergrad. And just as I started to learn more, and understand more, it suddenly became something that was much more possible. And then going beyond that, being an entrepreneur and starting up my own companies, it does seem like a bit of a pipe dream, but it can happen, and it can happen to you if you want to. From a long time, I've realized that the way we do industry now is fundamentally unsustainable. And I was kind of involved in climate activism from the age of about 14, and kind of wanted to dedicate my life to this, because I want basically arrive in a world where we can have all the great aspects of modern civilization, but none of these negative consequences that are quite severe, and are potentially going to get worse actually before they get better. And graphene seemed to have so much potential. I came across it in the news when in 2010, I think, just as the Nobel Prize was won, and then started to think, well, this could be applied for so many areas. At that point, I wasn't even thinking of water, and as I said, I was more interested in using it for batteries and supercapacitors and other things. But when you have a new, because graphene is obviously not alone, as James was saying, there's a whole host of two-dimensional materials, and nanotechnology is really about getting to the minimum dimension of single atoms, and graphene is a single atom. But the new physics and the discoveries that can be made, not just by understanding graphene alone, but by combining it with other two-dimensional materials, these are really endless, and it's just adding another capability to the suite of nanotechnological materials that we have. That is just, there's so many things that can be out there, that are out there, and we need as many people thinking about it as possible, because these technologies have to be directed towards improving sustainability, reducing the humanitarian aspects of water scarcity, of climate change, mass migration. And food scarcity as well, which is really important for what Beanish is working on. So there's a lot of scope, and I just encourage people listening to think about how they could make an impact, because there's a lot of impact that needs to be made.
Absolutely, Sarah, and it's really interesting how that you have a personal motivation, as your generation probably has, about the future and sustainability, and how that came together, and you saw graphene as an opportunity quite early on, before you started your academic career to the level you have. That's a fascinating insight, actually. Thanks for sharing that. And then, Beanish, did you have that eureka moment with graphene? Did you feel that at some point it could make a big difference to what could be you would like to do?
So yeah, to be honest with you, during my PhD, so I never worked with graphene. So my PhD was more about polymer and peptide hydrogel. But in our group, there was my friend. He used to work with graphene, And I used to fancy, because the thing is that when he used to add graphene in his hydrogel, and the properties were suddenly like start changing. It was more about cell culture. And at that point, I was like, I want to explore graphene. But to be honest with you, lots of, PhD students are aware, once you come into your PhD, it's just like, it's not flexible. You can't work with lots of things. So at that point, I was really interested. But because from that simple experiment, when I used to see my friend and the results he used to get, I was like, okay, this material has capabilities to change like material property just by adding simple small quantity of it. So what I did, like basically when I started my own company, so then when I was working on it, then obviously that was a chance for me to try and see like how it will change the properties of hydrogel, which I already developed. And from there, I saw, yes, yeah, when I added in it, and then I realized, okay, it has a potential like to change like especially antibacterial properties, because that was the most important thing, because as like food security, so in indoor farming, 50% of food grow like it get wasted just because there are loss of algal and fungal issues. And because of that, we managed to tackle it. But it's just like slightly out of topic, because there are lots of graphene oxide that is from commercial. It's not a bad thing. Obviously, graphene can be sourced from different like mostly it is from graphite. But the thing is that what I realized, it can be sourced from green components. So for example, biochar, if you have heard about it, it has like certain components of graphene oxide in it. So I decided to go from that route. And then the thing is that what I realized, so there are lots of areas that needs to be explored. So there are lots of natural material that has graphene oxide in it, but it's not like sourced in a way it should be. So that is something I can say like it can impact like really in a great way. So it's just quite interesting like to work on that.
Yeah, exactly. I like the serendipity of observing a colleague, learning from that, making that application, and realizing it can do something quite exciting and take things forward. Thanks, Beanish. So a number of questions have come through. And in fact, I think Zeb's mentioned it already around energy, and people interested in battery technologies and solar panels and that kind of thing. So James, I just wondered, we talked a lot about this water conservation and Beanish's work in agriculture and vertical farming, etc. But to take it into the energy field, is there a role there for advanced materials and graphene? That's obviously a big ask and a big demand for that.
So yeah, clearly energy storage or energy delivery in the future is going to be a key area for us in the future. So as an example, I think there's questions around batteries. Graphene is an addition to existing battery technology. So lithium-ion technology, there's a lot of research looking about, for example, improving the packaging, improving the membrane, the cathode, the anode. So through the addition of graphene to existing battery technology, again, there's quite a lot of interest. I think the area that excites me more is probably not around battery, but they're similar to batteries, that of supercapacitors, I think Seb touched on. So a supercapacitor is the ability to rapidly charge and discharge, so a boost of energy, if you like, and then recharge rapidly. So any Formula One fans out there, this is the boost you get as you go around the lap, and then you can recharge through braking. So I think, for example, our buses, our taxis of the future will increasingly use something called a supercapacitor. So for acceleration and braking, they can do that, charge, recharge many, many times. Again, there's some really interesting work around graphene supercapacitors. And I actually think our future will probably have a hybrid. You'll still have battery technology in your car or your vehicle, but increasingly you'll probably have a supercapacitor or even a fuel cell that will complement that. So again, graphene can play a role in fuel cells. Hydrogen is a really interesting one. Again, for those who follow the news, there's a company in the UK who's actually launching a new hydrogen fuel source, and they're actually building a supercar with a graphene enhanced bladder to contain the hydrogen within the car. So again, advanced materials will play a key role, whether it's in the structure, whether it's in the actual battery or the supercapacitor, or by enabling you to do things in a different way. Again, just to give you one example there, why don't we build our batteries into the structure of our vehicles going forward? Again, if we can get a safer, something that doesn't break on impact, again, we could start to combine energy storage with our batteries in the future. So yeah, graphene advanced materials will play a key role. I think it's not just graphene. I think increasingly the other 2D materials will start to play a role in here. But yeah, Seb, I think it was touched on it. Graphene has this ability to operate what we call multi-functionality. So it can provide you both strength, but it also can do large surface area for energy storage, through to different thermal management or electrical conductivity. So it enables you to start to design or develop your systems in the future in a different way. So yeah, lots of possibility, and clearly you'll play a key role in supporting our sustainability agenda in the future.
Fantastic, thanks, James. Just notice a question here. Actually, Debbie Nelson says in America and US, they've just announced released first water shortages in caution in California, Arizona, and Nevada. So it's interesting where these issues do lay, and they've been expecting this for a decade or so. So the question would be, probably to Zeb actually, can you utilize membranes to treat wastewater? There'd have to be some scale, because those are quite big areas, I guess. So what's your views on that?
Yeah, well, it's quite right. This is kind of what I was talking about earlier, the fact that 2 in 3 people experience severe water scarcity for at least 1 month of the year. And so California has had some very severe droughts over the last decade. And so it's put a lot of money into new desalination plants. In a way, there's kind of 2 things we need to do to solve this. One is we need to be more efficient at using the fresh water that's already existing. And that might be, innovations in agriculture, because as Beanish said, the majority of water, fresh water, is used for growing crops. And so, but you also want very sunny places to grow crops. And so sunny, dry places are often drought ridden. The other option is to simply, and part of that is also recycling water. So reusing fresh wastewater, for example, and treating that so that you're not just, leaving it into the environment. We're thinking about whether it makes sense to have domestic filtration, for example, to have a small system that might be under your sink that recycles your grey water and either makes it potable or makes it suitable for other secondary uses, like watering your plants. Even something like that could make a big difference. If you stand in the shower with a bucket, and then at the end of it you pour your bucket and use that water to flush your toilet, you will save 30% of your water just by doing that. So it's a pretty low tech and fairly simple way. So there's a lot of low hanging fruit in saving water. However, we are also growing as a human population. We might reach 10 billion or so by 2050. And presumably our total water consumption is actually going to go up, and so for that we need desalination, and desalination has become much cheaper, much more efficient over the last couple of decades, and California do a lot of this, as do Saudi Arabia. So now today, every day, about 100 billion liters of seawater is converted into fresh water by the world's desalination plants. The problem is, as I hinted on in my presentation, is the brine, is the fact that you're producing this waste as a result of that. Not only the membrane waste, but you're also producing chemically laden brine, which has to be diffused safely back into the sea, and that's kind of disrupting systems and is a source of pollution as well. There is a project that I mentioned that we're doing with Japan. Coming up next month, actually, we're going to send our membranes over to there to actually trial a new, fundamentally different way to do desalination, which is quite exciting, and potentially could reduce the costs significantly, and actually eliminates the brine problem, which I see as being applicable to places like California. I can't go into many details, I'm afraid, at this stage, but using effectively our technology, using a different energy source, could potentially change the way this is done, and making it sustainable, making it powered by renewable energy is really important as well. Australia do a lot of desalination, and they've committed that all of their desal plants are going to be powered by solar. So they don't produce the solar themselves, but they buy solar from the grid, and at least pegging those kind of things, the water production with the renewable energy production together, helps to keep the carbon footprint of emerging and growing industries down. But yeah, innovations in wastewater treatment. Another problem with wastewater treatment is that when the sewage goes down into the gutters, it produces methane. Bacteria produces methane and nitrous oxide. And so actually something that's not really known about, but if you look at the reports of wastewater treatment companies, the majority of their carbon and dioxide emissions, or carbon equivalents, come from methane and nitrous oxide as a result of the actual distribution. So we're interested in sort of more decentralized water treatment that can basically treat the water before those potent greenhouse gases are even released. So it's moving. The industry is moving. How it will be in the future is not exactly clear. It will be different for different places. But we have a lot of technologies and a lot of new technologies that will help address this in a carbon neutral way.
Right. I mean, it's interesting though, isn't it? How we perhaps as householders can perhaps do our bit, use this very hyper local technology, put into our sinks and do some of that recycling in our own homes. And then it's interesting how the technologies need to link. James is talking about the energy and sustainability, sustainable energy, and how graphene can support that. That therefore helps with the desalination units in these places, where so that all this technology, all this innovation needs to be linked up really to improve its effectiveness.
Wastewater recycling is crucial, but I don't think it will be sufficient. I think we will be relying on desal as well.
Okay, brilliant. Okay, well, that's an interesting summary of that. So, James, if I could come back to you, just really to think how you might want to summarise the session, what you learned today, and there's a lot of questions, but a lot of questions very technical. I mean, Sam and Beanish have been absolutely brilliant in their presentations, in explaining some of that amazing science, the engineering, and you've answered a lot of the questions already. But if I wanted to find out more, because your interest should be piqued by after hearing what you heard today and how these guys are making a difference. What's the best way, do you think, James, that people could start to engage more with the graphene community?
I mean, first of all, watch this video or pass this video on.
Pass it on, yeah.
Learned a lot. I think for me, what was really interesting listening to Seb and Beanish in particular is you can come to Manchester to study, maybe undergraduate, maybe postgraduate. It doesn't have to be in the sciences. I mentioned the hackathon last week where people came in around innovation, and there was everything from scientists through to business students through to humanities. So it's not just about the science. There's a lot of activity across Manchester, from graphene to engineering to business study. So find out more through the university, through the website about studying. I'd encourage you to reach out to people like Beanish and Seb. I know they're very busy. They're both finishing their degree, but they're also trying to start up a business. So they're very much in demand. But again, there's a number of webinars and seminars that both the university run. I know Beanish and Seb speak at a number of other events if that's of interest. So yeah, if you want to study, but also if you want to be business, if you actually want to create a startup or a spin out, Beanish and Seb mentioned the Geek. You can actually have a base in the Geek if you have a small business or a startup. There are competitions in the university like the Eli Harari Award, but you'll find things like Venture First and other types of awards that are in Manchester. Innovate UK is a UK funding agency that can provide funding for a concept or an idea or a scale up. So yeah, I would approach the university, approach people who are involved in this ecosystem, and find out some of the opportunities that you might have to either study in Manchester or get involved in a business or a startup or an enterprise that's involved with graphene. So I hope you found this useful and look forward to hopefully speaking or following up for a number of you in the future.
James, that's brilliant. That's great stuff. That's how I think many people listening will take up that offer there. That's a real great way to engage. Just as we approach the hour, and I can't believe we've gone for an hour. It's been a fascinating insight, actually. I really want to thank our panelists, James, Chief Executive at Graphene at Manchester, Beanish and Zeb, our two entrepreneurs, really all the best to you guys and what you're trying to do. I have to say, what I hadn't thought of until today is, we talk about Generation Z exactly. We now have the G generation, the graphene generation. People have grown up with graphene, inspired by graphene. You can see its potential and how that can motor their own ambitions towards sustainability. I think that's a really impressive message, and I'm grateful to have heard that. And I hope we can share that with our audience and beyond. So, yeah, just to sum up, just thanks very much, guys, for supporting today. Really great talk, and also to our audience today for participating. I know it's been a great turnout. Registration has been high, so obviously you guys have drawn in a lot of people today. Want to hear your story, and I think it's been a great one. So thank you very much.